Hello, welcome to chemistry class. Today we're going to talk about making solutions in chemistry, which is a key skill that any chemist would need to have. It's kind of strange talking to nobody in the room at the moment, but we're going to do this and hopefully someone will get some benefit from it in the future and be able to use the skill in your college class or maybe in your chemistry class in the future. So let me share the screen with you, and we will talk about how to make a solution. Then we're going to actually make one in class. So let's see what we can do here. Making a solution, a key skill for chemists. We're going to talk about some basic definitions of a solution, what they are, what are some key terms. Then we're going to talk about how do we know the strength of a solution, how strong is it. We're going to talk about a term called molarity, which you may or may not have heard of, but it has to do with the strength of the solution, and sometimes it's called molar concentration. And we're not talking about your back teeth, we're talking about the strength of a substance. And then we're going to talk about what is a mole. If I'm talking about molarity, there must be moles involved, which there are, but it's not the little animal that crawls around in your yard and digs it up. This is different. This is a measurement used in chemistry. Then we're actually going to make a 1 molar solution. Okay, solutions are homogeneous mixtures containing 2 or more substances called the solute and the solvent. Now, you may have heard of homogeneous mixtures because we've talked about that before, and maybe if you're from a different class, you've talked about it before, but mixing things together in which they're thoroughly combined and you can't tell one substance from another, that would be a homogeneous mixture. So, for example, if you mix sugar into iced tea or into, I guess, hot tea first and then stirred it up, you'd have a homogeneous mixture because you couldn't see the sugar versus the tea. It would all be one thing, one solution. The part that becomes dissolved, the sugar in this case, is called the solute. Now, you may not have heard of that term before, but a solute is anything that dissolves inside another substance. So the solute is the substance that dissolves. The solvent is the substance that does the dissolving, or it's called the dissolving medium. So in our case, a lot of times we use water as the solvent. So water is the thing that dissolves and does the dissolving for the solution. Most solutions are liquids. In our case, we're going to talk about liquids. Now, it doesn't have to be. Sometimes you can have a gas dissolved in a liquid. For example, anytime you open a soft drink, you hear the little hiss. You're allowing a gas to come out of solution because they have put carbon dioxide inside your drink to carbonate it. And then that is a carbonated solution of a gas in a liquid. Now, water is the most common solvent used in solutions, and hopefully from this demonstration, you'll see that you need to not assume that a clear liquid in your chemistry lab or even in your house, for example, don't assume it's water, because water dissolves, and a lot of times solutions look like clear liquids, but the solute that's in there inside that water could be dangerous to you, so you have to be careful. Okay, to form a solution, the solute particles have to separate from each other. If you put salt in water, it's not a solution until the salt dissolves or salt comes apart from itself. So we're going to look at a short video that kind of shows that. Now, in my picture here on the right, I've got salt in a spoon. You can see the crystals falling down into the water. They stay together for a minute, but then as they get further down, you see the water becomes a little murky, a little cloudy. Well, something's happening to the salt at that point. So the salt is actually dissolving. Now, salt dissolving in water happens pretty quick. If you've ever mixed those two together, you know that. So we're going to look at a short clip that kind of shows that. And you'll notice some of the subtitles in this are Canadian, which is pretty cool. And they show these little molecules of water. They look like little Mickey Mouse particles. And then you've got a big salt crystal off to the side. Now notice that the water and the salt are moving. Now sometimes we don't think solid things move, but their particles do vibrate. All right, if you look at the way they've drawn this picture, they've got a positive end of the water molecule and they've got a negative end of the water molecule. Now, if you know anything about chemistry, you know water is H2O. So on the negative side of the particle, that's the oxygen. And on the positive side, these two are hydrogens. So the oxygen is pulling the electrons over to itself, and it's making water a polar molecule. Now, you've probably heard water is polar, and people can tell me that in class all the time, water's polar. Now, we kind of just, describe, well, what does that mean? It means the oxygen is pulling all the electrons in the chemical bonds over to itself, and all that negativity goes over to the oxygen side of the particle. Okay, let's continue this on a little bit. And they'll show you the salt particles. Now, sodium is a positive ion and chlorine is a negative ion when they're combined together. So in salt, you've got that little red sodium particle and a blue chlorine particle. Now, they're not really red and blue, but in this video, they are. Okay, watch how the water comes in and grabs the opposite charge. And it's pulling the sodium and the chlorine out. And real quickly, we'll talk about that. Look at the chloride ion over here that became separated out of the salt particle. And then the sodium ion on the right became separated out of the salt particle. Notice how they show the water molecules turned opposite. Like the oxygens, the negatives are all turned towards the positive sodium because opposite charges attract. Kind of like if you rub your hair, a balloon in your hair, then your hair is going to stick to the balloon because of opposite charge. Okay, on the other side over here, we've got chlorine is attached to the positive side of water. So you've got all these hydrogens on the side turned toward the chlorine because positive and negative attract each other. So that goes on a gazillion times as the salt particle dissolves, because there are many, 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 many of those particles in there trying to be dissolved by the water. And there's many, many water molecules trying to get in there and grab the sodium and the chlorine. All right, so let's move this on. And in a second, they show you this happening on a big scale with a lot of water particles coming in there grabbing sodium and chlorine. And they're pulling those out. And look at how many, just think about, that's one salt crystal. Just think about that happening with a whole teaspoon of salt. Okay. So that's a pretty decent model that shows how salt and water dissolve each other. Now, we've never taken a microscope and looked at salt and water dissolving like that. This is a model, and models are used in chemistry all the time to try to help you, understand how things work. Okay, so let's continue with the discussion. Okay, so you kind of saw how the salt and the particles dissolve with each other, the salt and the water particles. How fast they dissolve, you could probably imagine this on your own. You don't need me to tell you that if you stir the salt or the sugar or the whatever that you're dissolving, you want it to dissolve faster, you stir it up. Another way you can make it dissolve faster is to heat it or to crush the solute. I could take the salt and crush it into fine particles and make it dissolve faster. So how fast something dissolves can be influenced by us. We can cause it to dissolve faster. imagine, you know, the picture that we saw earlier where you had all those water particles and those salt particles interacting with each other. Well, stirring and heating makes them move faster. So if they're moving faster, then they're going to dissolve faster. There's more collisions going on. Okay, how much solute dissolves? Now, you know, if you had cold iced tea and you put sugar in there, it's going to sink to the bottom, and you can stir and stir and stir, and it may not all dissolve. And if it doesn't, it's probably a temperature thing. If you heated the tea up, it might dissolve more. So dissolving depends on temperature and pressure, and then the polarity of the substances. We just looked at polarity, you know, whether it has a positive and a negative pole, or if it doesn't. Okay, some terms associated with solutions. Soluble means that substances will dissolve. A solute that's soluble will dissolve in a solvent. That's a tongue twister. So you need to learn to say that really fast. Okay, insoluble means a substance will not dissolve in a solvent. So in front of a word means not, so it's not soluble. Okay, if we're talking about liquids, like if I took oil and water and tried to mix them together, they are called immiscible. They don't dissolve in each other. They're going to separate back out. So two liquids that don't mix in each other, do not dissolve in each other, are called immiscible. If they do, like if you had isopropyl alcohol, which has water and isopropyl in it, then they're called miscible, meaning that they will dissolve in each other. You can look at rubbing alcohol and you can't tell where the water is and where the isopropyl is because they're miscible. Okay, if I want to know how much solute will dissolve, there's a term called solubility. It's how much will dissolve in a given amount of solvent at a certain temperature and pressure. Okay, this is a experiment that we did in class last year. We took and made, you know, several standard sugar solutions, and then we layered them in a test tube. We also layered them in a really big graduated cylinder, but you can see that they separate out. They're not mixed. The higher concentration or the more dense sugar solution is at the bottom, and the less dense is at the top. Now, they layer out that way. We don't have to make them. We just had to pour them slowly so they didn't mix. But they will layer and make that cool little density column there because of their concentration or how strong they are. So down at the bottom, we got the strongest liquid at the bottom, the strongest sugars at the bottom. And as you go up, every color is a different strength. And by the time you get to the top, it's mostly water. So very strong sugar at the bottom, mostly water at the top. And the strength is called the concentration. It's how much solute is dissolved in the water or in the solvent. We can measure concentration in different ways, but a very common way that's used in chemistry is called molarity. So molarity is a common way to measure concentration. All right, so molarity, let's talk about that. I went too far, go back. Okay, molarity means I've got to figure out how much solute is in every liter of solution. Well, liters, you kind of understand what liters are. You measure something with a graduated cylinder and you're going to get a volume in metric units. Now this will be milliliters, but you can convert it to liters. So liters of solution is the denominator. That's easy to get, you understand that. But what is a mole of solute? I don't know. Well, we know that the solute now is the stuff that's going to dissolve. So we just got to figure out what is a mole. How do we know we have a mole of something? Okay, a mole is a measurement used in chemistry, kind of like when you use dozens to talk about eggs. So if I have 12 eggs, I have 1 dozen. Well, that's a way to group eggs in a bunch. So if I got a group of eggs, I'm going to call it a dozen. Well, a mole in chemistry is a group of particles or a group of anything in the quantity of 6.02 times 10 to the 23rd. Well, that's scientific notation. So 10 to the 23rd just means I've got to move the decimal to the right 23 places. So if I have 6.02 times 10 to the 23rd ping pong balls or balloons or bowling balls or marbles or anything, if I have that many, then I can say I have a mole of those. Now that is a huge, huge number, and large objects like marbles would cover a tremendous amount of space if we had that many of them. So a mole is meant to measure particles you cannot see, like molecules or atoms. So if we want to talk about very, very tiny things that exist in huge quantities, then we're going to use this concept called the mole. And it's like saying there's 12 eggs in a dozen. There's 6.02 times 10 to the 23rd atoms in 1 mole of an element. Okay, so for example, a mole of water has 6.02 times 10 to the 23rd water molecules. A mole of apples has 6.02 times 10 to the 23rd apples. So a mole is just a counting unit that is used in chemistry to group particles that exist in huge quantities. So 1 mole of any element, we can figure out how much that is because, you know, chemistry is a practical science. You have to be able to measure out things and put them together and make solutions and do some, you know, some really cool stuff in the lab, but you've got to do it with counting out things you can't even see. So chemists have come up with this concept of the mole to help you do that, and also your periodic table. So we're going to have to use the periodic table to figure out how much mass do I need to measure out to have a mole, because I said we're going to make a 1 molar solution. So 1 mole of any element can be gotten by using a balance to weigh out its atomic mass. So if you've ever looked at the periodic table before, and I have one on the screen we'll look at in a little bit, but all those little decimal numbers that are on there, those are the atomic masses for the elements. And chemists have figured out that if I measure out the mass in grams of that element, then I'm going to have a mole of atoms of that element. Okay, the mole is named after Amadeo Avogadro, or in honor of him, and it's also called Avogadro's number. So you may hear people say that sometimes. It's Avogadro's number of particles. All right, so I told you we're going to make a solution. I'm going to move myself over here. And we're going to make a solution containing 1 mole of a solute. And we've got to be able to measure out 1 mole of the solute using a balance, because, you know, this theoretical stuff has to become practical at some point. So to do that, we're going to have to calculate how much the mass of 1 mole is for that solute. Now, I'm going to use a common solute, and it's called Epsom salt. So I've got some over here, and we're going to use it. And we're going to make a 1 molar solution of Epsom salt. Now you can make a 1 molar solution of any solute that you want to, and you do it the same way. If you know the chemical formula for it, you can figure out how much a mole of it is. So in this situation, we've got magnesium sulfate. That's the chemical name for Epsom salt. So this MgSO4 over here on the right, magnesium sulfate. Mg is magnesium, SO4 is sulfate, and this is the chemical name for Epsom salt. So I've got to take that chemical formula and break it down. So I'm breaking it down into magnesium, sulfur, and oxygen, and that's the components or the atoms that make up magnesium sulfate. Now what I need to know is the atomic mass of each one of those things. So if we flip over and look at the periodic table, then I've got to find magnesium, sulfur, and oxygen, and I got to look up the atomic masses. Well, magnesium, here it is, it's number 12 on the periodic table. Magnesium has an atomic mass of 24.305. Well, that's the number I'm going to use. If I had magnesium and I could mass out 24.305 grams, I would have a mole of magnesium. Okay, I also need sulfur. So here's sulfur over here on the right, number 16, and it has an atomic mass of 32.066. So if I measure it out on a balance and I get 32.066 grams of sulfur, then I have a mole. All right, and then oxygen's right above it, number 8, and it has an atomic mass of 15.999, and if I measure it out on the balance, which oxygen's a gas, so that would not be easy to do, but it's 15.999 grams in 1 mole. So if that kind of makes sense, we're going to go back and calculate the atomic mass for magnesium sulfate. All right, so let's go back here. And here's magnesium sulfate. If I calculate the atomic mass, then I'm going to take each one. So for my magnesium, I had 1 atom of magnesium in magnesium sulfate. I'm going to multiply that by the atomic mass, 24.305. Okay, in my chemical formula, I have 1 atom of sulfur. So 1, now if it was not 1, I would have to use a different number. And then my atomic mass, 32.066. All right, now oxygen. Oxygen has a 4 subscript. That means there's 4 oxygen atoms attached to sulfur. So I'm going to have to use a 4 times oxygen, 15.999. Now, if I multiply each one of those together and I get my grand total, that means add all of them up, I'm going to get 120.367. So 1 mole of magnesium sulfate would be 120.37 grams on the balance. I would measure it out on the balance. So that's how you do it. You're finding the molar mass is what it's called. When this process of taking all these elements and adding up their atomic masses by according to how many atoms are in the element, that's called the molar mass. So that's what we're doing. And 120.367, that's our number to have a mole of magnesium sulfate. Okay, so let's go to the next thing. All right, we're going to make a 1 molar solution. So there's certain equipment we need. We need a volumetric flask. We need a digital balance. We need a wash bottle, a spatula, funnel, barrel pipette. I mean, there's a ton of things we need. One thing I want to show you was something about temperature change when you make a solution. It's pretty cool to see, so I thought I would try to include that. But I have a thermometer here. We don't always need one of those, but I thought it would be neat to see. Beaker, stirring rod, whey paper, Epsom salt, and distilled water. Now we use distilled water when we make official chemical solutions because you don't want anything interfering with your solution. You just want it to be pure Epsom salt and water. And if you take water out of the tap, it's not pure. It's got chlorine and sodium, fluoride, and all kinds of stuff in it. So distilled water doesn't have all that stuff. All right, so we're gonna make this solution. Now to make the solution, we're gonna measure out the required amount of Epsom salt based on the size of the volumetric flask, put it in the volumetric flask and add some water. We're gonna swirl the flask to dissolve the salt because we want it all dissolved. And then we're gonna continue adding salt and swirling until it dissolves. And this volumetric flask, and here's one right here, we're gonna use it. You only fill it up to the mark. There's only one measurement line on this volumetric flask right about here in the neck of the flask. And you don't fill it up past that point. Because if you do, you've messed up your concentration of solution. This flask is made specifically to hold a certain amount of water and a certain amount of solution. So you want to fill it up to the mark and don't go past the mark. So that's how this works. We're going to make a standard solution. All right, I'm going to stop the screen share for a second. And move my video around so you can see what's going on with the stuff that I have here sitting in the lab. All right, so we're going to have to move the camera around a little bit so that you can see what's going on. and I'll describe what I'm doing, and hopefully you can see what you need to see here. Sorry about the moving. Hopefully it's not making you dizzy. Okay, so you can see a lot of my stuff that I've got here sitting in the lab, and if I need to move the camera again, I'll move it, but we've got the Epsom salt, we've got a balance, we've got just a ton of stuff here to do chemistry with, and doing it on camera is going to be fun. All right, so here's my balance. Here's my Epsom salt I showed you a few minutes ago. Here's the distilled water. I have water in a wash bottle that we use to clean the funnel as we put the salt down in the volumetric flask. Here's the volumetric flask. It's got a funnel in it, right there. Okay, so we're going to do this and measure out the amount that we'll need to make a 1 molar solution. All right, so I need to ask you something. We said that a 1 molar solution would be 1 mole of solute per liter of solution. Well, my flask is not a full liter. My flask is 500 milliliters. So if I have a 500 milliliter flask, then that's only half as much as 1 mole per liter. So I don't want to put the whole 120 grams into this half a liter because it's only half as big. So in other situations, like if you had a 250 milliliter flask, you'd have to calculate, you know, how much do I need to put in there to have 1 mole per liter, because I only have 250 milliliters, not a full liter. A full liter is 1,000 milliliters. So this is half of a liter. So if I need half a liter, then hopefully you can figure out that I need half of my mass that I calculated. So instead of the 120.367, I'm going to need 60.18 grams. So we're going to measure out 60.18 grams of Epsom salt. Now, I've got a watch glass here, which I'm using it to kind of stabilize everything. I'm putting it on the balance. Well, you know, I don't want to measure how much the watch glass weighs. So hopefully you know that you have to zero out the balance once you put stuff like that on there, that you don't want to know the mass of it. So also I've got a piece of wax paper that I use for weigh paper. I'm going to put it in there, and it's going to help me be able to transfer my salt into the volumetric flask without spilling it. So that's a key consideration. When you're making a solution, you do not want to spill a bunch of it, because if you do, that messes up your whole calculation. It messes up your strength. So I'm going to zero the balance. Okay, it's gone to zero, and I need 60.18 grams. I'm going to take some Epsom salt. Now, Epsom salt is not hazardous, but for good lab practice, I'm going to wear gloves. But Epsom salt's not hazardous. But in other situations, yeah, you wouldn't want to make solutions out of a strong base or an acid or something like that and not be wearing your lab equipment. It's there to protect you. So you make sure you take care of yourself. All right, so I'm gonna take some of my salt, and I've got a little scoop here that I'm using. It's easier than the spatula. And then I'm gonna start adding it to the balance till I get my 60.18. And it's going to be more than you think. It is a lot of salt. So that gave me about 17. So let's take this, and we got 24, 30. So that's about half what we need. 42, 47, 48, 51, 54. A little bit more. It's getting closer. I gotta slow down. 59.3. Okay. So I went just a tad over. I'm going to take just a scoop out with my spatula. Put it back in my little cup till I get my amount. 60.16. That's good enough for me. Okay, now good lab practice is after I've taken stuff out of the main container, I don't put it back in the main container because I might contaminate it. So I'm going to set that off to the side. All right, so I've got my Epsom salt. Now, if I tried to take all that Epsom salt, put it into this flask, and then start dissolving it, it would probably work. It might take a minute to get it all done. Plus, it is a lot of salt. So I'm going to start my process using a beaker first. And I'm going to put some water in the beaker and then start dissolving it there. And then I'll transfer it to the volumetric flask. Now I got to be careful because my flask only holds 500 milliliters. This is 1,000, no, this is a 500 milliliter beaker. So I do not want to fill up the beaker because I'll have too much water for my flask. So I'm going to do maybe halfway. Now, also doing this lets me show you something. So I'm going to be able to show you something about temperature. So I'm going to stick my little temperature probe in here and get the temperature of the water. And then I'm going to show you what happens when we add the salt. It's very interesting. Okay, so you can see right now we've got about 24 degrees Celsius. I'll kind of show you my lab quest, hopefully. So there's the graph it's making. Unfortunately, I've got my mirror is not on, so it looks backwards, but oh well, you can still see the graph. So we got kind of a steady temperature. So I'm gonna try to put this on the screen and let you see what happens when I add the salt to it. So maybe if I set this right there, and then I start putting the salt in there and dissolving it, you can kind of see what happens to temperature. So let's try this. Look at the temperature, what it's doing. And I'm not even stirring it up. I'm just dropping it down in there. Look at how the temperature is going down just because I put Epsom salt in water. So I'm gonna keep putting some of this in there. I'm not stirring it, so that's not telling me anything, that I'm not messing anything up or making it hotter by stirring it or anything. Look at how far down the temperature went. Made a really nice curve. Now I spilt a little bit of salt, so in class I'd be fussing at you because you spilt some salt, and that messes up your concentration a little bit. Not much, but a little bit. But in a real lab situation, or if you're doing this for a job or something, you got to be real careful. I'm balancing like headphones and LabQuest and balances, and it's just a lot of stuff going on right here in this little space. So I spilt a little bit, sorry. All right, so look at the temperature. Isn't that cool? I think that's the coolest thing, to watch this stuff happening, you know, in real life, and then being able to see what happens. So the solution's actually cooling off. So if I put my hands on the beaker, I can feel that it's cooler than the environment. So I'm gonna stir it up a little bit. Now see when I stir what it's doing to the temperature? Isn't that cool? Me doing something is, you know, disturbing it and making my temperature change. Now, maybe this helps you understand, why do we put Epsom salt in solution and then try to, you know, take care of our sprained ankles and things like that. So you make a solution of Epsom salt, you put your sprained ankle in there, or a bee sting or something like that, and it has this thing of, you know, cooling things off as it mixes. So we'll talk about that a little bit more later too. All right, so I'm going to put this into my volumetric flask, move my temperature out of the way so you can see. So I take my volumetric flask, put the funnel in it. I'm going to adjust the camera a little bit. Maybe you can see it. So then I want this to dissolve, so I'm going to stir it best I can. I may have to wash it out a little bit because I don't want to lose anything, any of this salt that I put in here. I don't want to lose it because it's important to my solution. So then I'm going to start pouring it into the flask. Remember, we're making a 1 molar solution of magnesium sulfate. So you can see that last bit is just some salt that hadn't dissolved yet. It's kind of goopy. Okay, so I'm gonna spray a little bit of water in here with my wash bottle and run it down into the flask. And this little beaker is pretty neat because it doesn't really hold a lot of residue on it. It allows it to slip right out of there, which is good. So now I'm using my wash bottle to wash the edges, the neck of the flask, to try to get some of that salt to go down in there. And now I'm going to swirl it. You can see I labeled it. Of course, you can't read it, it's backwards, but it's 1 molar magnesium sulfate. So in the lab, we label everything so people don't think that's just water. It looks like water, but that's not what it is. You saw us, we put salt in there. It would be worse for something like hydrochloric acid or sodium hydroxide, something strong. So as I stir it, and now I can feel the bottom of it's kind of cool to the touch. You can still see some salt swirling around on the bottom, but it's not as much. So I'm going to try to put some more salt in here. I'll use the spatula. I've got a wide mouth funnel, so it kind of channels everything good. I've got some chunks of salt that are making it a little bit harder. All right, so we've got to get all this salt down in there and we'll have a 1 molar solution of magnesium sulfate. Now I can, you know, dissolve it out and fill it up to the mark and all of that, and that's what I'll do to make it, you know, an official solution. And that's what you would do, and you would fill it up. Let me show you the mark real quickly. When you get to the end and you're trying to fill it up to the mark, you want to use either the wash bottle or a pipette. So at the very end, when I'm just wanting to put a few drops of water in there just to get me up to the mark, then I'm going to be adding it drop by drop to get it there. If I try to pour with a beaker or something like that, then I'm probably going to overshoot the mark and my whole solution will be messed up. So to get my right concentration, 1 molar magnesium sulfate, that's what I have to do. So I'm going to tell you just a few words about, you know, why the temperature was changing, and then that'll be it, because we're probably running a little bit long. All right, so let's screen share real quick. Okay, so if I'm looking at my solution that I made and I put the thermometer in there and the temperature went down, then I've got some heat transfer going on. And sometimes I can make a solution, I put my hand up there and it actually feels hot to the touch. That means heat's been given off. If heat's being given off, we call it exothermic. But if heat's being pulled into the system or into the flask, then we call it endothermic. Energy's going into. So imagine if you put your foot into an Epsom salt bath when you sprained your ankle, then any of the heat that's in your body, it's going to pull it into the solution and away from your ankle. So it kind of cools you off. So, you know, that's one of the properties of magnesium sulfate solution. But I hope you learned something about, you know, how to make solutions, how to make a standard solution. And, you know, these are used for a purpose to, for chemists to be able to make chemical reactions and all those kinds of things. So I hope you enjoyed the lesson, and maybe I'll get to talk to you again soon.